In this video, we're doing another example of visualizing a function of two variables. Just as a reminder, anytime you have a function of two variables, that's going to represent a surface. If I give you an equation representing a function of two variables, there's an implied domain there. For every xy value in that domain, we can plug that xy into the function f of xy, and we get a z value. Now when I sketch, if I want to visualize the graph of this function, I'm going to graph ordered triples x, y, and z equals f of xy. So this is going to give us a surface every time. Now there are two ways to visualize these surfaces. One way is to sketch what's called a contour map, or a collection of level curves, and we'll review briefly what that is. Basically it's like a topographical map. On each of the curves, you imagine that the z value is or the z takes on a certain value. So if z equals 10, you imagine it's 10 units out of the page. If z equals -3, you imagine it's 3 units into the page. And then through this collection of curves and imagining those z values at the appropriate levels, you can visualize what the function looks like in 3D. So we're going to sketch a contour map to get some sense of what's happening with this function g of xy. And then we're also going to look at our contour map and use it plus our knowledge of surfaces from previous chapters to sketch this surface in three-dimensional space. Okay, so let's start by sketching our contour map. The first thing you need to do whenever you sketch a contour map is decide on what the range of this is, because you need to pick z values in the range of this function. Well, notice it's a square root function. No matter what I put inside, whatever xy pair I put inside, there's going to be a number here. And since this is a negative number, and that's a positive number, and that's a positive number, there's going to be some domain where this is well defined. In that domain, this is going to be a positive number or possibly 0. So I'm just taking the square root of a number that's positive or 0. Well, if it's 0, we're going to take the square root of 0 and we're going to get 0. If it's not 0, the square root of a positive number is a positive number. So the range of g theoretically could be 0 to infinity, possibly, and this infinity is questionable. There might be an upper bound on that. It might not go all the way to infinity. But I know that I can't pick any negative numbers. There's no way I'm getting a z value out of here that's negative. So I want to pick small values of z near z equals 0, small positive values of z, and then see what the level curves look like. So I'll choose z equals 0, and I want these to be evenly spaced so that I get a good sense of how fast that z is changing as it goes from one level to another level. So I'll use z equals 1, z equals 2, and z equals 3, and let's do z equals 4 as well. Now, when I ask you to do this for a quiz or a test, I'm probably not going to have you do 4 of them. I'll probably have you do 3 of them, and one of them might be z equals 0, which is going to be very simple. Just keep that in mind. You just are going to have to pick out a few z values in the range, and you want them to be evenly spaced to get a good sense of the graph. But you're not going to have to do this much on your quizzes. So we set z equal to 0. And we get this. Now if I square both sides, I've got 0 equals 9 minus 4x squared plus y squared. Now if I rearrange that equation, I can see a little bit more what's going on with my surface. I am going to scratch those out for right now. I'm just going to focus on z equals 0. So let's subtract 9 from both sides, and we have this. And then let's divide both sides by -9, so it's got one side set equal to 1. The reason I do that is because I noticed I've got an x squared term and a y squared term, one negative, one positive. So this reminds me of my conic sections. My conics, almost always except for the circles, have one side set equal to 1. So I've got two variables squared. I want one side set equal to 1, so I divide everything by -9, and I've got this now. Or multiplying by 4/9, I can think of that as dividing by 9/4. I write it this way. And often when we're sketching these things, we like to have this as some number squared and this as some number squared. 9 over 4 is the same as 3 over 2. 9 is 3 squared. Okay, so now I see I've got a hyperbola, and it's centered at the origin. And this is when z equals 0. This is what we get. Now remember how this works. If it's centered at the origin, you're going to go plus and minus this many units in the x direction. So that's 1.5. So there's -1, or -2, -1, 1, and 2. And then here we're going to go plus and minus 3 units in the y direction. I hope I've left enough space for all of my level curves. Excuse me. All right, so we want to go plus and minus 1.5 units in the x direction, plus and minus 3 units in the y direction. And then remember, with hyperbolas, you're going to draw a rectangular box. This might seem a little strange, but I guess when z equals 0, we get a hyperbola in the xy plane. Now, since the y is negative and the x is positive, this is going to open in the x direction. Whichever variable is positive, that positive term is associated with the direction that the hyperbola's branches open. So the x is positive, so it's going to open left and right. It's going to look like this. That's what our surface looks like when z equals 0. And I'm going to label that for myself. That's z equals 0. I think we're going to have pretty much the same shape with all the other z values as well. So let's look at what happens when z equals 1. So I've got 1 equals the square root of 9 minus 4x squared plus y squared. Square both sides. And then subtract the 9 from both sides. So now you've got -8 on this side. It's no big deal. We'll do the same thing as we did before. So now I've got 1 equals x squared over 2 minus y squared over 8. And 2 is the same thing as square root of 2 squared. And 8 is the same thing as square root of 8 squared. I know you could simplify it to 2 root 2, but we're just trying to get a sense of how far to go in the x direction and the y direction. Square root of 2 is approximately 1.4. Square root of 8, I think that's 2.8. Yeah, about 2.8. Okay. So we want to go plus and minus about 1.4 units in the x direction and plus and minus 2.8 units in the y direction. So this was 1.5. For z equals 1, we're going to 1.4. Oh man, it's really close. And for z equals, and that's in the x direction. And then we're going to go 2.8 units in the y direction. So our rectangular box is going to look a lot like the other rectangular box. It's just a little smaller. And it still opens in the x direction. So I'm going to see branches that look like that. When I draw my hyperbolas, or excuse me, my asymptotes, that's what we get. Okay, I'm only going to do one more. I don't think there's any point in going all the way out to z equals 4. So let's do last one. Let's say so that blue one was z equals 1. And let's look at what we get when z equals 2. So this one's not particularly insightful. Square both sides. Subtract the 9 from both sides. 4 minus 9 is going to give us a negative 5. Divide both sides by negative 5. And you get 1 equals x squared over, and multiplying by 4 over 5, that's dividing by 5 over 4, minus y squared over 5. And if I want to write those as perfect squares, I can just write that as the square root of 5 over 2 squared minus y squared over square root of 5 squared. And square root of 5, it's a little bit more than 4, we know that. It's approximately 2.224. And half of that is approximately 1.1. So we're going to go 1.1 units in the x direction and 2.24 units in the y direction. So it's a little bit better, a little bit farther away. Hyperbolas are pretty much the same. And I'd like to draw branches in a different color. I'm going to use this orange. And remember, that is z equals 2. And say, okay, gosh, what's happening? Z equals 0 is here. Z equals 1 was very close and right next to it. Z equals 2 is a little bit farther away. What are we seeing? What is this surface? I feel like as z increases, we're getting closer and closer to the center. Something's happening there. Well, we're going to use this, and we're going to use our knowledge of surfaces from the last, or from a couple of chapters ago, to infer what this graph looks like. Now, let's take this equation and rearrange it so that it looks more like one of the equations from our previous chapter. That's probably the easiest way to get a sense of our graph. So we have z equals the square root of 9 minus x squared plus y squared. You're just replacing that g of xy with a z. And then you're going to square both sides. And you want to move all the squared terms to one side, because that's how these usually look. Remember our quadric surfaces. So we're going to have 4x squared minus y squared plus z squared equals 9. And then we're going to divide everything by 9. Of course, 9 divided by 9 is 1. Multiplying by 4 over 9, remember that's the same as dividing by 9 over 4. Be careful here though. This is not exactly equivalent. This is almost equivalent to this, but only under the condition that z is positive or possibly 0. So this is our surface, but we only get the part of the surface when z is positive. What does this look like? Do you remember? We've got two positives and a negative. All three variables are squared, and one side is equal to 1. Well, if we didn't have the restriction that z was positive, we would have a hyperboloid of one sheet. Remember, if you have one negative and two positives, it's a hyperboloid of one sheet. Because the negative is on the y, it opens in the y direction. And what we're going to see is just top half only, because we want the part where z is positive. So we're going to see something that looks like this. When y is 0, we are on an ellipse. It looks like we go, let's rearrange that equation a little bit. 9 over 4 is the same as 3 over 2. So we're going to go plus and minus 1.5 units in the x direction, plus and minus 3 units in the y or the z direction, or that's where we would go, but we're only doing the positive part. So it looks like this approximately. And then it's a hyperboloid of one sheet, so it's going to be larger over here. Now remember what it looks like in the xy plane. Oops, not that one. In the xy plane, it's opening around the y-axis, and we're seeing these cross sections in the xy plane. So we're seeing something that looks like this. It's very hard to draw these. Just do the best you can. That's all I do. That's all I expect of myself, is just to do the best I can. That's okay. But we're only seeing part of this. Maybe that part shouldn't be there. Oops, I'm so sorry. It was off the screen. So that's our hyperboloid of one sheet. Maybe a better picture would look like this. There's my x-axis, there's my y-axis, and there's my z-axis. And it goes up to z equals 3, and it goes up to over here to x equals 1.5. And I think if we look at these two pictures, that's consistent with our level curves over here. Z equals 0 in the xy plane, z equals 1. Gosh, we're really close to the same curve, but just lifted up 1 unit. Z equals 2. We're a little bit closer to the middle. Z equals 3, we're going to be even closer to the middle. Well, z equals 3, I think we're going to be up here. But then once we get beyond a certain point, when z gets to be 4 or above, the shape is going to change a little bit. But we're still going to see more hyperbolas. Hyperbolas in those planes where z is equal to a constant. All right. Now let's do one more. First I want to sketch some level curves. Notice that the range of h is definitely positive numbers. I'm going to say 0 to infinity, but I'm not 100% sure about the infinity yet. I just know that with a square root, I'm only going to get positive numbers out. So I'm going to say z equals this, and set z equal to 0, and set z equal to 1, maybe z equal to 2, and then see what our curves look like. If z equals 0, we've got this. That just means that 0 equals 16x squared plus 25y squared. And the only way that happens is if xy equals 0, 0. So we're good there. Now if we set one side equal to 1, you get that. Square both sides and you get this. I'd say, well, what does that look like? Well, if I rearrange it, multiplying by 16 is the same as dividing by 1/16, or 1/4 squared. Multiplying by 25 is the same as dividing by 1/25, or 1/5 squared. So that's an ellipse. It's a very small ellipse. I'm just going to go out pretty far. I'm going to call that x equals 1. And that x equals -1. And here's -1 in the y direction, +1 in the y direction. Now x goes from plus or minus 1/4 of a unit in the x direction. So we're going from here to here. So that's -1/4 and +1/4. And for the y's, we're going at 1/5. Well, that's 25%. I want to split this into 5 pieces instead and do 1/5. What about 20% of that? So I'm going to say 1/5 is approximately there. And so we have an ellipse that looks like that. It's just a little bit longer in the x direction than it is in the y direction. On this ellipse, z is equal to 1. On that one, that's just the origin right there. Z is equal to 0. On this one, set z equal to 2, square both sides, and then divide everything by 4. So you have 1 equals 4x squared plus 25y squared over 4. And I can rewrite that. Multiplying by 4 is dividing by 1/4. Multiplying by 25 over 4 is dividing by 4 over 25. So let's see what happens now. Ah, okay. So we're going to go plus and minus 1/2 of a unit in the x direction and plus and minus 2/5 of a unit in the y direction. So it's going to be the same basic shape, but that's 1/5. I want to go out to 2/5. I'm going to go to 1/2 in the x direction. All right. And I'm pretty sure if I increase these z's, I'm just going to get more and more ellipses. They're just going to get larger and larger and larger. So I've got a single point, an ellipse, a larger ellipse, and then another one. I think I'm either dealing with an elliptic paraboloid or possibly a cone. So let's see what we've got here. Because I've got z equals 0, z equals 1, that's 1 unit towards us, z equals 2, that's 2 units towards us, z equals 3 is going to be 3 units towards us, so it's just going to get it's going to get larger as it comes out of the page more. To figure out which one we're dealing with, let's take our equation, replace the h with a z, so we have z equals the square root of 16x squared plus 25y squared. You want to square both sides. So I guess this just implies it doesn't go both ways. Well, I guess it goes both ways if I have a restriction. As long as z is greater than or equal to 0, we're good. Because z is that positive square root. And then I rearrange the equation. I've got all 3 variables squared, so I put them all on the same side, and we get this. Ah, it is a cone. We've got 2 variables squared, or 3 variables squared, 2 positive, 1 negative, and a 0. And you have a 0, remember it's a cone. Now if you want, you can write it in this standard form. Multiplying by 16 is dividing by 1 over 16. And so you get that. All right, but remember, you're just talking about that part where z is positive. So we've got a cone that opens in the z direction, and we want just the upper nap, that top nap, the upper nap of the cone. And it's a little bit longer in the x direction than it is in the y direction, but they're very similar. So you might not be able to tell that it's longer in the x direction than the y direction. So maybe it just looks, that's very rough, like this. So that's our cone. Z equals 0 is right here, z equals 1, right there. Z equals 2. Would be there. Z equals 3 would be up from that, and so on. And so this time, our surface is the upper nap of an elliptic cone. So make sure you're prepared to graph those surfaces from the first chapter, and you can see how the relationship between these level curves That's z equals 0, z equals 1 is 1 unit up, z equals 2 is 2 units up, and this surface. We did that for this one. We also did that for this one. Its graph looked like that. And then in the last video, we looked at a very simple example, the elliptic paraboloid.